for advanced study in Princeton for a few years. He made it out of there, is now working at Johns Hopkins University with Mark Kamiankowski in his group. And he will soon be departing Johns Hopkins for a faculty position at New York University in the fall. So we'll join the theoretical Center for Astrophysics and something.
Particle
yeah. Center for something or other, right? Okay. So it's a pleasure to have him here. He's going to be talking about dark matter and primordial black holes. I should actually mention, about a year or so ago, him and his group wrote a paper on primordial black holes, trying to explain the gravitational wave signal from LIGO, and that sort of reinvigorated this idea that primordial black holes could be dark matter, and there's a bunch of papers that have followed up on that, really thanks almost 100% to that effort that he was part of. So, take it away.
Thanks. Thank you very much for having me here. It was a nice introduction. When I went to the IS, Mark actually told me you have to do your time there.
Yeah, right.
So I will talk mostly indeed about primordial black holes, but I will also tell you a little bit about sub-GeV dark matter, so more of a part like the standard particle dark matter paradigm, but non-wave dark matter. And I will show you how one can use the CMB spectrum as a direct detection experiment to prove interacting dark matter. So let me start with an express review of CMB physics for the non-CMB physicists in the audience. So there are two aspects of the CMB. The first one is the global, if you take the sky average, the angle average of the CMB, and you look at the spectrum, the frequency spectrum of the CMB, so the intensity of the function of frequency. So this is a nearly perfect black body. It's as good as a black body as the Virus calibrator. And Virus has set very stringent upper limits on the deviations, and I will explain what these parameters mu and y mean, on deviations or spectral distortions from a black body. So what do we learn by not seeing any deviations from a black body? What's the underlying physics? So basically, if you inject heat or photons at redshifts higher than about 2 million, these heats or these photons get fully thermalized by double Compton scattering rupture. Okay, so what would result in this is you still have a black body spectrum, just with a slightly different temperature, that is not necessarily observable as a distortion to the CMB. If some heat or photons are injected between redshift of 50,000 and 2 million, which 2 million corresponds to like a month or so after the Big Bang, this heat or photons are partially thermalized by Compton scattering. So double Compton and rupture can no longer efficiently create or destroy photons, but Compton scattering can efficiently change the photon energy. And you end up with a Bose-Einstein distribution with a non-zero chemical potential, regardless of the details of the injection mechanism. So this is this mu parameter that Virus has constrained to be less than 10⁻⁴. If you then inject heat at redshifts lower than about 50,000, even Compton scattering is no longer efficient to redistribute the energy efficiently. So the detailed shape of the distortion depends on the detailed mechanism. But for specific mechanism where you heat, for example, baryons, which then exchange heat with photons through Compton scattering, you get a so-called Compton Y distortion, which is the same as the anisotropies distortion. Okay? What I just want you to get from these is that the amount of the amplitude of the fractional distortion, either mu or y, is basically the integral over time of the rate of energy injection normalized to the energy density in the CMB. Okay, so this is just a dimensionless number. And the type of distortion just depends on the redshift range of the energy injection process. So these mu and y distortions are just two limiting cases of continuum of shapes of the distortion. So the bottom line is that Virus tells us that no process has injected more than something like 10⁻⁵ of in terms of fractional energy of CMB energy into the plasma, starting 2 months after the Big Bang. Okay. There is a proposed mission, PIXI, led by Al Crockett, which will, if it is launched, reach sensitivity of something like 10⁻⁸. So if your orders of magnitude better, so hopefully we can learn lots about the early thermal history of the universe with these better precision. So that's the first aspect of the CMB that is not often discussed in great detail in CMB courses, I would say. The second aspect that's probably more known because of more modern experiments that have measured it to great precision is the anisotropies of the CMB. So here, what we measure is the temperature. So we assume a perfect black body at every point in the sky, and we measure how the temperature varies spatially. And what we measure is the power spectrum of the temperature, i.e. the variance of the fluctuations as a function of angular scales. So several satellites, including Planck, have measured this to better and better precision. The underlying physics here has two basic ingredients. So if you're given some initial conditions, first you have to evolve dynamically the perturbations, i.e. the coupled evolution of the metric, dark matter, neutrino, photons, and baryons. So this is done by Boltzmann codes like CMB fast, CAN, or class. And the second aspect is cosmological recombination, which is something I worked on during my thesis. The idea here is that the moment this visible diffunction gives you the differential probability of last scattering of CMB photons. And so knowing exactly how the universe recombined as a function of redshift gives you the details of this curve here. And the Planck satellites, to get the measurement of the Planck satellite is basically at the 0.1% level around the peak of last scattering. So one needs to understand this function at about 0.1% level to extract cosmological parameters to the precision. Conversely, if you modify the recombination history, this can be seen, this can have an impact on CMB anisotropy, and so this can be used to constrain any non-standard recombination history. For instance, the bound that probably you are familiar with, so the bound on the annihilation cross-section of dark matter from the Planck satellite comes from effect. So if the dark matter annihilates, this would change the recombination history, hence the visibility function, hence the CMB anisotropies. Okay, so this bound here comes from this effect. Okay, so this was for the brief introduction. And now let me tell you about two different, very different models that one can constrain through the scene. So the first one is about sub-GeV dark matter particles. What if they interact with center-wall particles? Can we see anything on the CMB? This is work with Jens Kuhlmann, Mark Minkowski, and the final money plot here is that we get upper bounds on the cross-section of dark matter interacting either with photons or electrons and protons as a function of the dark matter mass. So why is this interesting? Direct detection, there are of course many direct detection, there's a huge effort in direct detection experiments. So with the current constraints on dark matter nucleon interactions, basically hit a wall around a GeV or so, and the reason is that the dark matter needs to be heavy enough that it provides sufficient recoil energy to the nuclei in the detector. There are also limits on dark matter electron interactions, and here the process is that the dark matter can actually excite or ionize electrons in the target medium. And so the energy required is lower, and so you can actually constrain this electron dark matter cross-section down to 10 MeV or so. And again, below this, the dark matter doesn't have enough energy. What I want to emphasize is that both of these figures are sensitive. They have folded in some assumptions about the local, on Earth, dark matter phase-space density, dark matter density and velocity distribution. And so, at least from the point of view of a purely phenomenological question, there's no reason to stop at the GeV or 10 MeV. And so, but there's actually lots of efforts in direct detection experiments to try and go lower. And so what I'm going to show you is that we can actually say something about these lower masses from the CMB. So there are, first of all, there are limits that were worked out by various authors from CMB anisotropies, so the spatial or angular independence of CMB temperature and polarization. The underlying physics here is that if the dark matter interacts, say, with baryons, then it can exchange momentum with baryons, and so this leads to modified fluid equations in this Boltzmann codes. So this has no effect on recombination. This is an effect on the dynamical evolution of the perturbation. So just schematically, this is a purely Newtonian, in the Newtonian limits, this is the baryon momentum equation, so this is the coupling with photons, and here you would add an additional coupling momentum coupling with dark matter, and similarly for the evolution of dark matter. Okay, so this has been used to set limits on the dark matter baryon section, for example. So the effect is to suppress the anisotropies at small scales. Effectively, the dark matter adds baryon loading, for those who are familiar with this. And so the best limits, as far as I know, for masses much greater than GeV, because things become slightly more complicated to implement for lower masses, were derived by Hopkins in this figure here. What I want to point out is that CMB anisotropies are sensitive to multiple moments L up to about 2,000 or so, which corresponds to maximum wave number, okay, of about 0.2 inverse megaparsecs or so. These wave numbers enter the horizon at redshift less than about 60,000 or so. So the CMB anisotropies are not very sensitive to whatever happens before redshift of 60,000 or so. So the dark matter has a velocity, the interaction has a velocity or energy dependence such that the interaction was strong at high redshift, but then coupled later on, you would not see it in CMB anisotropies. Similarly, if you use, for example, the Lyman alpha forest, this probes smaller scales, so you're sensitive to high redshift, but still not as high as CMB spectral distortions. So let me explain how CMB spectral, so again, this is now we take the spatial average of the CMB and we'll look at the intensity as a function of frequency and how this differs from black body spectrum. So what I explained briefly in the beginning is that if you inject energy into the photon bearing plasma, this could lead to distortion. So now I'm talking about elastic scattering of a dark matter particle with standard model particles. So how can this inject energy? So the basic process is as follows. Photons cool down adiabatically. If they were on their own, their temperature goes as 1 over the scale factor, i.e. 1 plus the redshift. Now if you have a non-relativistic particle, for example, the dark matter particle, but this also works for baryons, it would cool down adiabatically. Temperature would go as 1 over the scale factor squared. If these two species are scattering elastically with one another, they become put in thermal contact, and as a consequence, there will be not only momentum exchange, as we discussed, as was used for CMB anisotropy probes, but there will also be a heat exchange. And because of the steeper dependence here, the net heat flow will be from photons to the dark matter. So the effect is that the CMB will, some heat will be extracted from the CMB because it will be giving it to this dark matter particle that cools down faster. The effect basically is if in the extreme limit where the dark matter is thermalized, then the CMB temperature goes as 1 over the scale factor to the 1 plus epsilon, or this epsilon is basically the ratio of the number density of dark matter particle to the number density of photons. And I want to point out that this effect exists in the standard universe to replace dark matter by baryons. So what if the dark matter, so this was if the dark matter scatters directly with photons, if it scatters with electrons, we have the same story. There's an indirect thermal coupling to the photons through Compton scattering. So dark matter scatters with electrons, exchange heat to the electrons, and the electrons exchange heat to the photons. So the photons give heat to the electrons, which then give it to the dark matter. Same thing if the dark matter scatters with nuclei. We have now 2 levels of indirect coupling, but it's the same story through electrons, through Compton and Coulomb scattering. So the bottom line is that the fractional energy extracted from the photons by this dark matter that can scatter elastically is proportional to this epsilon, so the ratio of number density of dark matter to photons, times some log of some initial redshift to some final redshift. Now, first of all, we know, so if we assume that this particle makes 100% of dark matter, what we know is not the number density, but rather the mass density of dark matter. So this is inversely proportional to the mass of the dark matter particle, which is why you expect it to be more sensitive to light dark matter particles. The maximum redshift is about 2 million, otherwise, as I said before, whatever happens before 2 millions, any injection, or in this case, extraction of energy is fully thermalized, so it only leads to a change in the temperature of the CMB, but not distorted. And finally, this redshift here is the redshift at which the dark matter stops exchanging heat with the photons. and it decouples thermally from the photons. And so this is where the microphysics is hidden. I mean, this depends on the cross-section and the mass of the dark matter particle. So plotting this, okay, I'll put another plot so that makes it not. So if you invert this relation and say this is less than, say, 10 minus 5 for 5 mass, then you get these limits in the solid curves. And if you invert this relation saying it has to be less than 10 minus 8, as this once you given by Pixie, that sensitivity of Pixie, you would be able to extend these limits to higher dark matter masses. These are shown here. I'm showing constraints just for constant cross-section, but we also have in the paper constraints for different velocity or energy dependencies of the cross-section. So these limits here only apply to masses less than about 0.1 MeV, and again, this is because of this prefactor here, that it can only get so large if you have a heavy dark matter particle. So it's not necessarily very interesting limit in the sense that there are other limits from the number of effective degrees of freedom that would apply for dark matter particles less than an MeV or so. But this is still an independent limit. And those limits would be much more interesting because they could cover the gap that is not covered by direct detection experiments. Even if the amplitude here is much higher, this is a much cleaner probe in the sense that you are not dependent upon the local dark matter density and velocity distribution.
Could you draw like direct detection, maybe like there's some dark matter electron bound.
That's the electron.
Less than a GeV.
That's the electron bound.
That's the electron bound.
And I didn't.
I thought actually that extends. Oh, sorry, that's MEV. I'm sorry. Okay.
Right, that's the electron bound, and then
okay.
the nucleon bound would start around
Okay.
here. That's why I didn't draw it.
I have a question as well. So why your bounds are better for proton and electron? Because 5 minutes ago you were saying that regardless of what channel they interact with, you always have better.
Right. Well.
Lower mass. Why it goes down? Why your limit is better at higher mass for proton and electron than for photon?
Oh, why it goes down this way?
So it means that you're more sensitive now. So going
Right.
higher.
Okay.
Is that because of just the mass matching between the
So you see that there is a kink basically around the mass of the electron here.
Yeah.
This is just of the kinematics. I don't have in my
So you have a number density and kinematics.
You have the number density that is really just simple kinematics, and you calculate the energy exchange in an elastic scatter. And so the mass comes in there.
I feel like I should know the answer to this question. Where exactly does the Milky Way satellite bound come in?
Right. So this is a paper, I should have put the reference here, by Céline Bohan and collaborators. The bound here is, so if you have dark matter photon interactions, you will have again momentum exchange between dark matter photons. So now we're talking about the perturbations aspects, not the global vicinity spectrum. So this would decrease, this would add as, if you want, like a pressure force on the dark matter. So this would cut off the small scale dark matter perturbations. And so you would have less Milky Way satellites.
The missing satellites are
So yeah, then you would have even more missing satellites than what we see. So this is how they derive this bound. So this is, I would argue, very clean bound, the CMB spectrum.
Yeah.
Even though, of course, it's going to be really hard to measure the CMB spectral distortions to 10 minus 8 or so. Okay, so let's move on a very different mass scale. This was sub-GeV dark matter. Let's move to primordial black holes. So, as a brief introduction to primordial black holes, so the idea of having dense objects around has been around for a while, but I think the first paper that sort of formalized the idea of primordial black holes in a more modern sense of the term is by Stephen Hawking in 1971. So the first aspect that he mentions is the formation process. The idea is that primordial black holes could have formed as a result of relatively large primordial perturbations in the universe. And I'm not going to give you more details because I'm not an expert at all on this aspect. The second piece in this paper, without saying these specific words, but Stephen Hawking basically points out that this could be the dark matter. It is tempting to suppose that the major part of the mass of the universe is in the form of collapsed objects. This extra density could stabilize clusters of galaxies which otherwise appear mostly to not be gravitationally bound. And a third interesting thing from a historical point of view is that this Hawking suggested that primordial black holes could have explained the gravitational waves that had just been detected back in 1970. So, for those who don't know, Joseph Weber claimed detection of gravitational waves in 1969, 1967, and so Hawking said, well, this could be small black holes that go inside of stars, and I don't know the exact process, but then they eventually make the stars blow up. So it's a very different mechanism than what I'm about to talk about. So this is just for the brief historical introduction. So primordial black holes have been a model for dark matter for a long time, and as Louis just mentioned, these were recently revived by the LIGO detection of merger of roughly 30 solar mass black holes. So in a paper led by Simeon Bird at Hopkins, we asked LIGO the question, did LIGO detect dark matter? And I'm going to explain this a bit more. And another paper by another group basically also proposed that primordial black holes could lead to gravitational wave, to a merger rate similar to what is inferred by the LIGO collaboration. The two mechanisms, which I'm about to describe, are very different. So in this paper, the basic idea is that if two black holes, 2 point masses for what matters, pass sufficiently close to one another, they can lose energy through radiation of gravitational waves. So this is very similar to radiative recombination for atoms, except that instead of being electric dipole radiation, it's a quadruple radiation of gravitational waves. And so there's a well-defined cross-section for this process. From this, you can estimate the merger rate per halo by integrating sigma v times the number density squared of objects, and you get something that depends on the halo mass, the halo density, and the characteristic halo velocity dispersion. Then you integrate this rate times the halo mass function. So you need to assume some mass function. So what we do in this paper is we assume some basically pressure sector or something similar to pressure sector, like a Tinker mass function. We also need to assume some concentration relation, i.e. how does the density of a halo depend on the mass of it. And from this, we use simulations which apply to mass ranges vastly different from what we apply it to. And we extrapolate over orders of magnitude.
That's not necessarily true.
What do you mean?
I think you're giving yourself too little. I mean, you're talking about like 30 solar mass objects or whatever, right? And some of these simulations have resolution of like, hundreds of thousands of solar masses, right?
Well, the simulations that give you the concentration mass
Oh, that's true. Okay, yeah.
apply to like
The large scale ones, okay.
10 to the 9, 10 to the 10 solar mass halos, and we're going down to like a few hundred solar masses. So
yeah, so the large scale, yeah, when you get where you get the statistics of the mass function, yeah.
yeah,
That's
the mass function and the concentration, etc. And we need to cut off this integral, which is divergent. And so to cut it off, we cut it off basically halos such that the evaporation time and the time scale it takes. So the halos become collisional if you have sufficiently few objects, and then basically this velocity distribution becomes Maxwell-Boltzmann, and then as time goes on, some fraction of the objects gets kicked out of the halo. So we cut this integral about 400 solar masses, which corresponds to like a dozen primordial black holes. So with all these assumptions, we get a rate which is about 1 gigaparsec per gigapascal per year, which is roughly consistent with LIGO's inferred merger rate, which is about 2 to 50. Okay. So I want to point out that this is an order of magnitude estimate and maybe an orders of magnitude estimate. Okay? So we're not claiming that LIGO detected dark matter, but pointing out an interesting rate coincidence. Okay. So we got some interesting fan mail. Someone bumped their fist and yelled out, yes, and encouraged us as valiant astrophysics warriors. So with such encouragement...
Is that person an astrophysicist?
I don't think so. So follow-up led by Elias Chorlitz was to compute the distribution of eccentricities of these primordial black hole binaries, and the main point of this paper is that something like 1% of the binary mergers should have high eccentricities when they enter the LIGO band. The prospects for LIGO are very weak to detect this very small percentage, but with the Einstein telescope you could see a little more. What I'm working on now is to correct an important piece that we neglect in the paper, which is the fact that on small scales, if you have dark matter made of 30 solar mass objects, you have a huge Poisson noise on very small scale. So this is the variance of fluctuation in the function of halo mass. This is the standard variance which we use in the paper, and this is the actual variance once you're on clean shot noise. So it's order of magnitude higher. So as a consequence, it changes completely what are the characteristic densities, velocities of the halos, for example, and as a consequence, the merger rate per halo also is very much increased if you account for the Poisson noise. So initially I thought, okay, this is going to bump up the rates by orders of magnitude. However, it also changes the evaporation time, and so now we need to cut off the integral not at a few hundred solar masses, but rather at a few tens of thousands of solar masses. And so the total merger rate, so this is per log m, actually is something like just 1 order of magnitude higher. So within the orders of magnitude uncertainty, this effect does not change the results very much. Let me go over quickly the scenario of the other groups, Sasaki et al. So this is based on their original paper by Nakamura et al. in 1997. So the idea here is that, again, on very small scales, the black holes are effectively randomly distributed, which is what gave us the Poisson shock noise I showed in the previous slide. So there is some chance that a given pair of black holes is so close that it's effectively decoupled from Hubble expansion at basically before matter radiation equality. Okay. Now, this pair would collide directly if there was no tidal torques from the other black holes. So one can estimate the eccentricity, which is related to the angular momentum, as basically the tidal torque from the nearest third object. And so in this paper, they have basically a distribution of semi-major axes and eccentricities from which they find the distribution of merger times, and from which they can find the rate of mergers at the present time. So now, in our scenario, binaries basically form in present-day halos and merge within much less than Hubble time. In this scenario, we have almost primordial binaries that form at matter radiation equality or before, and very slowly inspire and merge continuously, and some of them merge today. So their approach is, in order to get the LIGO rates, merger rates, they show that if the PBHs make just a very small fraction of the dark matter, something like 10⁻⁴ to 10⁻�3, then they would get the LIGO merger rate. And so this fraction corresponded to the best CMB bound as of 2008. Okay, so this is why this is an interesting coincidence, because then we can, if we improve the CMB bound, we can actually rule out this mechanism. So what I will show you is that the CMB bound actually, I think, goes away. So let's briefly review the constraints that exist on primordial black holes. So this is the mass of the primordial black hole, either in grams or in solar masses, and the maximum fraction of the dark matter. So on very small masses, there are limits due to the fact that these black holes evaporate. And Stephen and collaborators and we have reworked this. I don't know if it corresponds to this.
It's a little bit stronger.
It's a little bit stronger. So the idea, I don't know for these limits, but their paper is that if the black hole evaporates, you can heat up and ionize the gas, and hence have an effect on the recombination history, hence on CMB limits. So I'm not going to look at explain all the limits, but so the most famous ones are microlensing, the wide binary bound here around starting around a few like 100 solar masses. The idea is that there are wide binaries in the galaxy, and if you had machos or any sort of compact objects, they could disrupt these white binaries, and so the distribution of some major axes would have a cutoff at some large major axes, and so this can be used to set the limit. And finally, the CMB bounds by Massimo Ricotti and collaborators really were the strongest bound, excluding significantly the dark matter as PBHS around 30 solar masses or so. So I will get into this in great detail.
What was DF? I forgot. What's DF?
DF dwarf? No, it's not DF. What is DF? I don't know.
That's Chris Fine.
I thought it was dwarf galaxies, but I'm not sure. This one, I think, is Shorty and Spurlow et al. It's like short noise and that.
Okay.
But I don't remember what it does.
Oh.
Okay, so what I'm going to explain the last half hour is how I derive these plots. So this is revisiting. So this is the previous limits from Ricotti, Tracker, and Mack on the CMB limit on partial black holes, and these are the limits I derived. This is the sort of conservative limit. The actual limit within this model would be lying somewhere between these curves. These two curves are also to illustrate that this is a very uncertain physics. I want to emphasize right now that the underlying physics is the same as in this paper. Okay? Plus, of course, ingredients that were not accounted for. But the basic model is the same. So the basic physics is as follows. Primordial black holes accrete baryons. Some fraction of the accreted mass gets re-radiated. Some fraction of this luminosity gets deposited in the photon-bearing plasma as heat and as ionizations. The fraction that is deposited as heat could lead to CMB spectral distortions, as explained earlier on. And the fraction that is deposited as ionizations can change the recombination history, hence the visibility function, and hence the CMB anisotropies. And so the game is just to quantify each one of these steps. So the philosophy is, because this is an extremely complex problem, the black hole accreting gas, I have no expertise in this. So the philosophy is to derive the minimum physically plausible luminosity in order to get the most conservative bound. Okay? So the bound is saying that whatever is above the bound is for sure excluded, but what is below may be excluded if one were able to do a more detailed calculation with simulations, etc. Yes, and what I also want to emphasize is that the bounds, even if conservative, are still order of magnitude bounds. So do not, it's not because the CMB anisotropies are measured to 0.1% precision that these bounds claim any of the precisions. Okay, so let's not mix CMB with the precision of the bounds. So first step is to estimate the accretion rate. Okay, so let's do simple estimates. First of all, we're going to make the assumption that it's steady state. This is self-consistent, we'll show in the paper, shown by Ricotti et al. For masses up to a few tens of thousands of solar masses. So the bounds only apply to this regime. Whatever is above is constrained anyway. We're going to assume spherical accretion. Why? One, because it's very simple. Two, because it's very difficult to estimate the angular momentum, because we're talking about scales which are much smaller than any observed scale. Okay, the characteristic scale at which the accretion takes place is much smaller. Second, finally, the reason why we assume this is that typically if you have an angular momentum, accretion with angular momentum, you get an accretion disk, and typically an accretion disk leads to a higher luminosity. The reason is that a significant fraction of the rest mass has to be radiated in case of a disk accretion, whereas for spherical accretion, there's no need to, as you will see, it's just free radiation. So this should be the conservative hypothesis in the sense that again, it's a lower estimate of the luminosity. Black holes are not standing still with respect to the baryons, so if they are the dark matter or some fraction of the dark matter, we know that the dark matter has large relative motions with respect to the baryons on large scales. And so clearly the accretion is not spherical. The black holes see some incoming flow of baryons. So this is not analytic, so we'll need to have some hack for this. And so what we do is we replace sound speed by square root of sound speed squared plus relative velocity squared. Same as Ricotta et al., same as Bondi-Hoyle. We will neglect thermal feedback, so this black hole radiative luminosity. We show that it is self-consistent to neglect thermal feedback for lighting of black holes. And I'm about to explain what we do with the ionization feedback. So this luminosity of the black hole could also have an effect on the local ionization fraction around the black hole. Okay, so the accretion rate is basically generalizing the Bondi-Hoyle-Lyttleton accretion model, which, so this model is based on papers from the 40s and 50s. So again, it's very simple. Again, it's steady state, spherical symmetry. So this is just a mass conservation equation. This is just a momentum equation. And in these papers, they assume a barotropic equation of state. So P goes as rho to the gamma, where gamma is a constant. From pure dimensional analysis, you can show that the accretion rate has to be proportional to the Bondi radius squared, which is Gm over sound speed squared, okay, times rho times sound speed. So just from pure dimensional analysis, this is how the accretion rate is. And this constant lambda depends on gamma and can be computed explicitly with this signal. So there are some characteristic scales in this problem. The Bondi radius, as I said, Gm over sound speed squared, and the Bondi time, which I'm going to use later on. So how do we generalize this? We have accretion of baryons, but in a universe that is full of photons. And these photons have very important dynamical effects. First of all, they lead to a drag on the baryons. So the baryons cannot just fall into the black hole. They have a strong drag because of Compton scattering. Secondly, the pressure is not just barotropic. It is basically just the ideal gas law. And so the evolution of the temperature here depends on Compton cooling. So if Compton cooling was negligible, this would just tell us that T was as rho to 2/3. So then you would have a adiabatic pressure density relation, but in practice, Compton scattering cools down the photons to try and maintain it at the temperature of the scene. Okay. So in the Ricotta et al., so this ROM is Ricotta et al., the limit that was assumed is isothermal, i.e. very strong Compton cooling, which allowed them to set T equals to TCMB here. Now, this is the ratio of the Bondi time scale to the cooling time scale. So when this ratio is large, indeed one can assume an isothermal equation of states. But when this ratio is small, which is the case for low mass primordial black holes and at low redshift, then one cannot assume this. One has to, the equation is mostly adiabatic. So we explicitly compute this lambda here, but generalize it to having this Compton drag and Compton cooling, and this is what you get. This is the accretion rate normalized to basically Eddington luminosity. Just for you will understand why I'm using this later on. So this is to show at first the effect of this first physical assumption that was not accounted for. The isothermal approximation typically overestimates the accretion rate by up to a factor of 10 at lower redshifts. We will see in just the next slide that the luminosity is quadratic in the accretion rate. So that can be already a factor of 100 degrees. So we have the accretion rate. How do we compute the luminosity? So we want to find the radiative efficiency, i.e. this parameter that relates m dot c squared to the luminosity. So if you have just spherical accretion, the minimum luminosity comes from free. So you may have shocks and whatnot if it's not spherical, which may increase the luminosity, but the simplest assumption is that it comes just from free radiation. This free luminosity is quadratic in the electron density. And so I recall that the accretion rate itself is, so in steady state it's just 4 pi r squared rho v, and close to the black hole Schwarzschild radius, is just basically proportional to 1 times t squared. So all this just to say that if I replace this ME here by m dot divided by all that stuff, you can show that the luminosity is quadratic in m dot c squared. Okay, that's just the reason why I'm showing all this. So the luminosity is quadratic in m dot c squared, and it also depends on the temperature of the gas near the horizon. So the next step is to estimate this temperature. So what we do here is to generalize the simple model by Shapiro, 1973. So what Shapiro did is to compute the numerical solution of steady-state relativistic fluid and heat equations around the structure of a black hole. And he considered two cases, either a fully ionized black hole, background with a temperature of 10 to the 4, or neutral black background with a temperature of 400. And here I'm showing the temperature as a profile as a function in these two cases. So our equation model, so first there are simplifications, so I'm not going to do a fuller relative simplification because, again, this is just an order of magnitude calculation. And this, the relativistic corrections would just matter very close to the horizon, and so we're going to do like this. We will assume that, so here, this plateau here, if you start with a neutral black background, is the collisional ionization region. Okay, so basically, the gas self-ionizes through collisions. And this, as you can see, happens roughly at constant temperature and temperature by 10 to the 4. So we will assume that collisional ionization proceeds at a constant temperature, neglect any other cooling process during its phase, and just by using the first law of thermodynamics, you can actually have exactly the shape of the ionization density profile throughout the ionization. So extension of the model is to have, yes, this very simple analytic approximation for arbitrary ionization background. We'll also account for Compton cooling. And we will consider two cases for the local feedback on the ionization state of the gas. Let me explain this. So what was considered in Shapiro is just this collisional ionization case. So if you have a partially neutral background, once the temperature reaches about 10 to the 4 Kelvin, the gas gets collisionally ionized. Now, the black hole, again, is radiating, has some luminosity because of its accretion. So there's another extreme case where the luminosity of the black hole creates a stronger sphere around the black hole that extends farther than this collisional ionization region. In which case, we're in the limit where the gas is locally photoionized by the black hole. So we consider these two limiting cases. We show in the paper that the extent of this stronger sphere by the black hole is never as far as the Bondi radius. So basically, it does not affect the first part of the talk, which was about accretion rates. So to compute m dot, the accretion rate, I assumed a constant free electron fraction. I did not worry about whether it is affected by the luminosity, and we show it's self-consistent. What we show, however, is that so the luminosity is typically lower in the collisional ionization case because this decreases the thermal energy of the gas. So collisional ionization decreases the thermal energy of the gas, hence the luminosity. So we show, if we assume this case, that the stronger radius extends somewhere inside the collisional ionization region, which means that this case is not self-consistent. If we assume the full photonization case, that the luminosity that we infer from it also extends not all the way, but somewhere inside, which means that this case is also not self-consistent. The bottom line is that we show that neither these two limiting cases is self-consistent, which is why the limits I get, the actual limit is somewhere in between. Okay. Temperature profile, okay, the basic points of the temperature profile. Outside, the temperature of the gas is coupled to the CMB temperature of the Compton cooling. Once it decouples, it gets compressed, the gas gets compressed adiabatically. The temperature goes as rho to the 2/3, which goes as 1/r. Once, in the collisional ionization case, once the temperature reaches about 10 to the 4 Kelvin, it plateaus, the gas gets collision ionized. Then it increases again as 1 over r until electrons become relativistic, at which point the adiabatic index changes and the temperature goes as 1 over r to 2/3. If we assume instead this photonization case, there's no collisional ionization region, and we just go from 1 over r to 1 over r to 2/3. And so in this case, you have, as I said, a larger temperature, hence luminosity. One thing that we add that is not in Shapiro's paper is the effect of Compton cooling. So what Compton cooling does is that it maintains the gas temperature equal to the CMB temperature if you increase it down to a smaller radius, which lowers the temperature close to the Schwarzschild radius. Okay. So we plug all this together, and this is the temperature as a function of redshift for different black hole masses in these two limited cases. So what you see in this plot, these are basically the same results as Shapiro's, up to factors of 2 or 3, with much simpler, actually, calculation than Shapiro's, but within a factor of 2 or 3 we get the same results. This decrease here is the effect of recombination, which implies that the background gas is mostly neutral, which then leads to collisional ionization region, which, as I explained, decreases the temperature of the gas. And this decrease here is due to Compton cooling, which imposes that the gas temperature is equal to the CMB temperature deeper inside the accretion region. Okay, so these are the characteristic qualitative features of this curve. From this, we extract the radiative efficiency, which again is defined as the relationship between mass, accretion rate, and luminosity. And so this radiative efficiency itself is linear in dots. This dimensionless parameter here was assumed to be about 10 minus 2 in the previous work, and we find it is at most 10 minus 3 in the null. Okay? So this is another reason why we get weaker constraints, is because of this efficiency, which we compute from first principles, although of course with a very simplified model. One more point, as I said, baryons and dark matter have relative velocities. The origin of this relative velocity is that before recombination, baryons and dark matter have very different dynamical evolutions. So the baryons are coupled to the photons, and together baryons and photons undergo acoustic oscillations. On the other hand, the dark matter perturbations just grow rapidly. And so they have very different characteristic densities at recombination, they have very different characteristic velocities around recombination. And it turns out that the characteristic relative flow between baryons and dark matter is about 30 kilometers per second at recombination, which is actually supersonic. It's Mach 5. So this has some effects on the growth of very small scale structure, which was pointed out by Tzedek and Murata. Yes, and after the recombination, basically baryons become cold and the relative velocity just increases as one rate. So in our case, so we're only going to account for linear, for this piece, which is linear, large scale motions, but of course, we have black holes that may get bound into halos, etc., and this is very hard to estimate, so we're not going to deal with this aspect. So the bottom line is, as I said, we use a simple hack, which is to replace in all the accretion rate and then the luminosity, etc., the sound speed by this square root of sound speed squared plus relative velocity squared. This is unpleasant, but it's the best we can do from an analytic point of view. Then we average the luminosity over the Gaussian distribution of its relative velocities. So just to give you an idea of how much this leads to a decrease, as I said, luminosity is quadratic in the mass accretion rate, which in the Bondi case goes as 1 over the sound speed cubed. So this scales in this way with the relative velocity. So if you average this function over a supersonic relative velocity distribution, it turns out that the suppression, so if it's Mach 5, the suppression is about a factor of 100. Okay. Now, in the previous work, Ricotti et al. Assumed a significantly smaller relative velocity. And so, again, we get a factor of up to 100 because it's redshift dependent. up to 100 suppression just by taking the correct relative velocity. Okay, so this is just the luminosity, and to illustrate, because it's an important point to check, that is everywhere less than Eddington luminosity. Okay, so to recap up to now, so lots of steps. The first step was to compute the mass accretion rate, for which we used the Bondi-Hoyle model, but to which we added Compton derived and Compton. The second step is to convert mass accretion into luminosity, from which we used Shapiro model, but to which we added arbitrary ionization background and Compton cooling as well. The third step is now we have some source of luminosity, and it's free luminosity. So we have a characteristic temperature, which was about MeV-ish. The free spectrum is roughly flat up to MeV-ish. The question is now, I have this source of MeV-ish photons. How do they actually get deposited into the plasma? Because if they just travel without depositing their energy into the plasma, they will have no effect. There will be some gamma ray background. So the dominant deposition mechanism for these photons is Compton scattering. So Tracy Slatcher, for example, and collaborators have detailed codes on how to follow the deposition of photons of given energy into the plasma. Here, we do something simpler, but actually should give you rather accurate results. So we write a simplified Boltzmann equation for the number density of photons per energy bin. This NE here is the number density of photons per energy bin. Okay. If there was, so this term is the source term, this is basically what is injecting by the PBHS. This term is the deposition term. So this is basically the rate at which Compton scattering loses, at the rate at which photons lose energy through Compton scattering. This is a very simplified sort of continuity equation, if you want, for the photon intensity. This scaling here is just that if this was 0, this number in an expanding universe should go as 1/8 squared. Okay? So now, as such, this is already a very simplified equation. Normally, you should have some sort of integral differential equation. To simplify it further, let's look at this quantity. So this is the Compton cross-section, which has a very well-known energy dependence, and this delta E is just the change of energy in Compton scattering, which also is a very simple kinematic problem. Okay? And yes, this is what you're saying, that this is just the source term. So this is this sigma delta E divided by sigma Thomson times E. And the point of this plot is just to show that this function is actually very almost constant around an MeV-ish. Why is that? In the Thomson limit, this sigma is sigma Thomson. However, the delta E is small. Okay. And in the ultra-relativistic limit, the delta E is a further E, but the sigma is less than sigma Thomson. So it so happens that around MeV-ish or so, which is the energy scales we're interested in, this is roughly constant, and we shall take it to be about 0.1, because why not have one more approximation? And if you do this, then this equation simplifies a lot. And then to extract the energy deposition rate, given this energy injection rate, you just integrate the photon spectrum times sigma delta E. And the bottom line is that you have arrived at a very simple ODE for the deposition rate given the injection rate. Now I want to point out that several works, previous works, including some where I was an author, had a wrong integral solution. Well, not even integral solution. No one wrote this equation, but had what should have been the equivalent of this equation in an integral form, but with incorrect scales. So this is the ratio of the deposition rate to the injection rate. So at high redshift, it goes to unity. The energy is basically deposited on the spot. And at low redshift, the energy is inefficiently deposited because the number density of the gas number density decreases. And you can show that it scales as from 8 to the -7. So I should conclude quickly. So bottom line is that CMB spectral distortions, which are computed, as I explained earlier, by integrating over time the deposition rate over the energy density of photons, you can show that this is much lower than Fire's limit, and even Pixie will not be able to say anything about primordial black holes within the model that I described, which is very similar to our map. The main effect is hence not the CMB spectrum, but rather the effect on recombination history. So how do we implement this? We implement this by, this was first done by Chen and Kamikoski. The idea is that, so this is the rate of energy deposition. Some of it will go into heating the gas. Some of it will go into directly ionizing the gas, and some of it will go into exciting neutral hydrogen atoms. So this I implemented in my recombination code, HIREC. This is just to show you how this leads to an increase in the free electron fraction as a function of redshift, depending on the fractional PBHS and their mass. And this leads to an effect on the CMB anisotropies. The effect is qualitatively similar to a change in the, to an increase in the reionization optical depth. It suppresses the anisotropies on CMB anisotropies on small scales, and it leads to an increased polarization power spectrum on large angular scales. So it's qualitatively similar, though not quantitatively. So this is the details of the analysis. You can look at the paper, but basically we actually use Planck data for high L, simplified Planck-like code, and account for the low L's with prior on tau reionization. And so this is how, with all these steps here, that we derive these bounds. The most conservative one, if you assume collision ionization, and the correct bound within this model lies somewhere between these two. Okay? And so the most conservative bound says that black hole with masses above 100 solar masses or so cannot make 100% dark matter. Now, I would not take this slope very, very seriously, because one thing we did not account for is that if black holes make a fraction of the dark matter, one is to ask what is the rest of the dark matter. And so what was done in Ricotte et al. Is to say, well, the rest of the dark matter is WIMPS, and those can form halos around these black holes, and hence can increase the diffusion rate. So the slope would be steeper, but the intersect would be the same. Okay, so to conclude, primordial black holes do not distort the CMB spectrum within the simplified model. However, CMB temperature and polarization angular fluctuations could be affected for black holes greater than 100 solar masses, and so we use this to set limits. I want to emphasize again that these are subject to very large theoretical uncertainties. Right, one last point I wanted to show that I mentioned to some of you yesterday is, well, so now if the CMB is no longer a limit, the Sasaki et al. Paper, so basically this is the plot from this Sasaki et al. Paper, where they have a very different scenario. This is the event rate, and this is the LIGO window, as a function of the fraction of dark matter and boundary black holes. And so what they had said at the time is that if you saturate, this was the CMB bound at the time, they said if you roughly saturate the CMB bound, you roughly are within the LIGO window. Now that the CMB bound is essentially gone, we can turn this around and say, well, if this result is correct, then actually we can turn around this calculation and set a very stringent upper bound on the abundance of boundary black holes because of their non-detection by LIGO. So that's something I've been working on, because what was not looked at in this paper is what happens between the formation of these boundaries and the present time. And it's very likely that they get disrupted or torqued by the time. So that's something I'm working on now. And the reason why I think it's interesting is because if you just plotted again this limit here on this plot, it would actually be a very stringent one. So what I'm working on now is checking that this still applies and see how this can be extended to different masses. All right, this took a little bit too long.
have no feeling if there's a mass function coming out of this, of the black holes. I mean, you're focusing on one specific black hole, the 30 solar mass black
Right,
hole.
right, yeah.
But there's got to be a mass function somewhere,
Yes,
right? And
yeah.
so, do you have any guess as to what that mass function
So,
is?
it's very unlikely that it should be like a single mass for, I think, any formation scenario. I think the two problems are decoupled. How black holes get formed and what is their mass function versus what limits can be set from a purely phenomenological point of view. So I have been concerned more with the latter. But all these bounds indeed apply to a single derived mass function. In some cases, for example, well, I don't know exactly how you would generalize it for other cases, but for the CMB, it would be easy to just change the direct mass function by any arbitrary mass function. But yeah, I haven't at all looked at the sort of the production mechanism.
Question I see you mentioned. So I think this idea of like, so when you write that paper by Scholz et al., like where he calculated sort of the average eccentricity distribution for captured black holes. So I have a feeling there's going to be some like equilibrium process here. I think you said you were trying to calculate this, whether like what's the rate at which the black hole binaries form relative to the rate at which they're destroyed, right? In a given dark matter halo.
Right.
So I guess sort of.
Or just torqued rather than
Yeah. So so I guess maybe going back to the Scholz paper. So what's did he calculate sort of the average eccentricity and timescale distribution?
Right.
He calculated the average eccentricity and calculated the timescale for a black hole to get captured and merged. Is that
Right. So I also have checked. So now that I'm checking this paper, I also checked ours because we also didn't check if these black holes get torqued or whatever.
Yeah. So there's like so really this actually becomes. And you said I think you're working on this. Like what's the what wins? Like do you preferentially just blow apart? The binaries.
So I think you don't blow them apart. So in the case of the Bird et al. Or the Scholz paper,
yeah.
I checked that there's not enough time basically between formation and merger to affect the binary significance.
Okay,
These
that's
are
what I'm
highly
asking.
eccentric
Okay.
binaries, so they merge very quickly.
They merge very quickly.
In this scenario, what I have checked so far is that I think you're safe with respect to the energy, or so you cannot destroy. You cannot ionize the binary. You cannot easily change their energies, but what is worrisome is the angular momentum, because the merger timescale depends very strongly on the angular momentum to the 7th power. And so if you just slightly increase it, circularize the binary a little bit by other torques, then you can completely change the merger timescale and make them merge in much longer than normal time. But such worries, I checked, don't apply to the vertical scenario.
I guess the comment too, that ultra-faint dwarf balance comes from it. This is the Brand's and theoretical analysis, but that was most recently applied in Aerodonist et al. Paper that Tangle had, I guess. So should rework that based upon whether or not you blow up a star cluster in Aerodonist. Just have one more small question. So, do people need to go back and revisit this intermediate mass black hole merger question? This is probably at lower frequencies, right? If I remember correctly. So wasn't there like people who calculated sort of stochastic backgrounds of mergers of intermediate mass black holes to become more massive black holes?
And by intermediates, you mean?
Whatever, 10,000 solar masses. And there was speculative papers long ago about what's the stochastic gravitational wave background from mergers of like proto-galaxies, like with intermediate mass black holes and something like this. I think these feels like papers somebody's written before that I've ignored because there's a few tooth fairies involved here.
What would they
Do we need to revisit? I mean, I guess like this, you have a formalism here, right? You can actually apply this to those
to
calculations.
this intermediate.
Yeah. I think they're lower frequencies.
It's the same formalism because here it's really you have a bunch of point masses in a halo and they happen to pass close to each other. They're like thermalized.
Mm-hmm.
In this case, it's more like a standard merger tree for galaxies.
I guess if you have like globular clusters with black holes in them or something.
Sorry?
If you have globular clusters with like intermediate mass black holes in them.
Yeah.
Oh yeah, I guess you're right. It's not exactly the same thing. But I think that is lower frequency.
I think so.
Anyway. All right.